Battery is a small battery for traveling. You just have to, it means that you need the charger all the time. I'm going to ask these guys if they could provide the charger.
Yeah, that'd be nice.
One less thing to carry.
Hey Al, did you have any announcements you wanted to make? Okay, so let's get started. Last lecture we started talking about noise. So last lecture we looked deep down and device noise, where it comes from. Today's lecture we're going to take the opposite viewpoint. We're going to look from a high-level perspective. What does noise do to a communication system, and what are the common metrics to describe noise in a communication system? Okay, so last lecture we were talking about noise in analog communication systems. There it's very obvious what noise does, right? It adds static to a voice conversation or to a music. If you're watching television, you see snow on the screen, and so on and so forth. It's a very qualitative measure. And depending on what sense you're talking about and who you talk to, different levels of basically noise can be tolerated. So for instance, the eyes tend to tolerate a lot more noise than the ears do. And the eyes, for instance, tend to be very forgiving to low-frequency noise, whereas the ears are sensitive. Some people characterize this by saying the eyes are kind of taking the average and the ears are kind of taking the difference. So the ears are very sensitive to even high-frequency noise, whereas the eyes average them out. Anyhow, this is not a class on psychology. What we're going to look at is basically the signal-to-noise ratio. Is a very important so what we're really interested in is the SNR. So SNR is basically the signal power divided by the noise power. In other words, the bigger it is, the better. And so qualitatively we could say that for good, let's say, voice communications, you should have at least, let's say, 15 dB SNR. But we can make that a lot more quantitative if we look at digital communication systems. So in digital communication systems, and many of you guys have studied digital communication systems, you know that there's a characteristic waterfall curve that looks something like this. So on this axis we have the bit error rate, and on this axis we have the signal-to-noise ratio. And this is a log-log scale. So let's say this is 0 dB, 10 dB, 20 dB, 30 dB, 40 dB, and so on. In other words, at 30 dB, the signal is 1,000 times more powerful than the noise. Then on the y-axis, we have the bit error rate. So this would be a bit error rate of 1. If you're always making errors, it's not a very good communication system, right? This is a 10%, let's say, error. This is a 1%, 0.1%, and so on. And depending on the modulation scheme you use and all the details of the communication, what the channel looks like, at the end of the day, you end up with a curve that does something like this. And this is the characteristic waterfall. The idea is that if your signal-to-noise ratio gets, let's say, less than 10 dB in this particular example, communication becomes pretty painful. Every 1 out of 10 bits is going to be an error. Depending on basically the amount of coding you have in the system, you may be able to tolerate different amounts of errors. For instance, a 1% error rate is pretty tolerable. You can put coding in your system. 1 out of 100 bits comes in error, but if you have codes, you can correct for that. So you can see on this curve that requires more than 10 dB of SNR. Now this is just an imaginary curve I drew here, but you can generate curves like this for different modulation schemes. And as a circuit designer, the system designer will tell you, look, you have to, under all conditions, worst case conditions, you have to guarantee, let's say, better than 10 dB SNR. So that's the spec you get from the system designer. Okay. Now, just to be a little more specific, SNR, because it's the ratio of powers in dB, it's the ratio of the power of the signal divided by the power in the noise. Okay. I know in office hours there's been lots of questions about dBs and dBms and dBcs and 10 logs and 20 logs. It does get confusing, especially when the impedance can be anything, right? Is it 50 ohms? Is it 500 ohms? Is it 75 ohms? If you're ever in doubt, convert everything into real numbers and just work with real numbers. Okay. All right. So let's define the noise figure. The noise figure is a very important metric, and it's basically a measure of the degradation of the SNR due to a two-port block. And by a two-port block, I mean it can be an amplifier, a filter, or anything else. But mostly it's going to be amplifiers, mixers, blocks that take energy at one frequency and put them out at another frequency. So for an amplifier, for instance, this would be the measure of the signal-noise ratio at the input divided by the measure of the signal-noise ratio at the output. So by definition, it's the SNR at the input divided by the SNR at the output. Okay? And some people call this the noise factor. And then they call the noise figure basically 10 log of F and express it in dB. Okay? In this class, we'll use both terms interchangeably. It should be clear in context what we're talking about. So if I say what's the noise figure of an amplifier, usually it should be given in dBs. Okay? So this is a very nice definition. There is a little bit of ambiguity in it here, because what's this SNR at the input, right? The SNR at the input is something that basically we have no control over. So you have to specify that this F is defined where the noise of the source, or the noise at the input, is due to a 50 ohm resistor at 293 Kelvin. Okay, so just by definition, this is just a definition. We say your source is a 50 ohm resistor and it's at 293 Kelvin, and that's the noise being generated at the source. Okay? So let me show you guys graphically what noise figure is. So graphically, here's my amplifier. And let's say that I have a certain input signal. So I'm going to draw the spectrum, the power spectrum, at the input. So let's say the power spectrum at the input looks like this. This is the signal power. And let's say this is a dB scale. And this is the noise power. So in dB, this difference is the SNR at the input, right? Now what happens when I go through the amplifier? Well, if this amplifier were noiseless, what would happen is both the noise floor would go up by the gain of the amplifier, and the signal level would go up by the gain of the amplifier. Unfortunately, the amplifier is not noiseless. It adds its own noise to the output. So what we see is that the gain goes up, the noise floor goes up, and the signal goes up, but the noise floor goes up faster than the signal goes up. So this is now the SNR at the output. Here, this is the SNR at the input. So now this is the GP times power of the signal. This noise floor here is G times power of the noise of the source plus the noise of the amplifier. Okay? And you can see that this SNR is smaller than this SNR. And the difference between these two on, again, a dB scale is the noise figure of the amplifier. So if my SNR reduces by 5 dB, that means the noise figure of the amplifier is 5 dB. Okay? Is that pretty clear, the definition of noise figure? So if you understand this picture, you understand everything there is to know about noise figure. What we're going to do for the next 2 lectures is just calculate noise figure under different circumstances. But the key point is this picture. So if you have any doubt in your mind about this picture, now is the time to ask, because that will make the next 2 lectures a lot more pleasant. Okay? All right. Well, in terms of numbers, I can say the SNR at the input is some signal power coming in, right? And as we'll see, the signal power doesn't really matter. We'll see that it drops out. And let's call NS the noise power. This is the noise of the source. Okay? This is NS here. I should be consistent with my notation. All right, now the SNR at the output is GP times the power of the signal divided by GP NS, right, plus noise of the amplifier. And I'm going to call this noise of the amplifier at the output. And we'll see why a little bit later. Okay? Now if I take the ratio of SNR at the output to SNR at the input to SNR at the output, you'll see that P signal cancels out. So let me do that. So by definition, F is SNR input divided by SNR output. And I can tell you last time when I taught this course, I saw a lot of people write SNR at the output divided by the input, right? We're so used to signal out over signal in. Don't make that mistake. You'll get the wrong answer. If you ever get a noise figure that's negative, you know you've done something wrong, okay? In dBs, or a noise figure less than 1. Which, it's a good time to say that a perfect noiseless amplifier has a noise figure of 1, right? That means the SNR at the input is the same as the SNR at the output. So we'll come back to that. All right, so coming back to this calculation, I have P sig divided by NS times GP NS plus noise of the amp at the output divided by GP P signal. That cancels out, and so I can write F is equal to 1, right? This is GPNS divided by GPNS plus N amplifier at the output divided by GP divided by NS. Okay? And so this you can just call noise of the amplifier at the input. Right? This is the noise divided by the gain. So this is the input referred is noise of the amplifier, the output divided by the gain, or it's the input referred amplifier noise. Okay? In other words, this looks like if I have an amplifier, so this is some noisy amplifier, I can just take my amplifier, make it a noiseless amplifier, and then just add N amp input to the input. Okay? So this is the input referred noise just being added to the input, and now I can assume my amplifier generates no noise. Okay? Yes, question?
Is the GP of signals necessarily the same as GP for the noise?
That's a good question. That's actually a very good question. So you have to be really careful what this GP is, right? This is the power gain, and the power gain is calculated assuming some kind of impedance matching. So hopefully by the closer to the end of this lecture, we'll come back to this point. For now, let's just pretend like we're system people, we don't know anything about circuits. Okay? All right, we'll come back to that point. All right, so based on this new noise of the input, I can just write this as 1 plus noise of the amplifier at the input divided by NS. Okay, so let me copy that equation here. So now I have that the noise figure, or the noise factor if you like, is the noise of the amplifier at the input divided by NS. Okay, and because that was such a bad drawing, let me try one more time. So I've modeled my amplifier, amp with no noise. This is N amp input, and then I have my signal coming in, and I have my noise coming in, which I call NS. Okay, so let me draw it like that. That's my noise coming in. And so, just as you would expect, as the amplifier input referred noise goes to 0, the noise figure approaches 1. So F is equal to 1 for a noiseless amplifier. Okay? So if anybody tells you they have an amplifier with a noise figure less than 1, you know they're smoking something. Okay? Any questions? Comments? Okay, so we'll come back to this, but you can think of the noise as coming from two places, right? If I take my amplifier and I just ground the input, right, and I hook this up to a spectrum analyzer, right, this will give me the noise floor at the output of the amplifier, right? So this is what I call noise amplifier output. Okay? Now I can pretend like my amplifier has no noise. Okay? And at the input, I'm adding N amp input, where N amp input is the amplifier noise at the output divided by the power gain. And now my amplifier doesn't have any noise, and the noise figure now we see is just 1 plus the ratio of how much noise you add relative to the noise of the source. So if the amplifier has 10 times more noise than the noise of the source, the noise factor is going to be 11. Okay? All right. Glad you asked that question, because I want to make sure these definitions are clear. Okay? Any other questions at this point? All right. Well, what if you have a cascade of blocks? Okay. Based on the machinery that we've developed so far, this is a pretty easy problem to analyze. So I have two amplifiers which are connected in cascade. Let's say the first one has a gain of G1 and a noise factor F1, and a gain G2, noise factor F2. And these are unilateral amplifiers, very simple. We assume they're impedance matched to each other. And I want to now look at this as a block. Okay? And so I know the overall gain is going to be G1, G2, assuming there's impedance matching. And what I'd like to find is the F of the overall system. So again, I have some P sig coming in plus NS, and I want to find the noise figure of this total system. So the first assumption, I'm going to assume impedance matching. So that's the total gain. Makes the calculations much simpler. Okay? All right, so now the observation is that for each amplifier, I have a noise figure which is 1 plus the input referred noise, let's call this J, of the jth amplifier divided by the standard NS, right? So I know this is true for each amplifier. In other words, I can solve this equation for the N amp input for each amplifier in terms of its noise factor and NS. So let me just do that. So I can say that N amp Ij is Fj minus 1 times Ns. Okay? So this is all just by definition. And so now I can think of my system as follows. I have, this would be N-amp1. This would be, this is F1, this is F2. This will be F2 minus 1 Ns, which is N-amp2. And this one is F1 minus 1 times Ns. Okay? So now what I can do is I can input refer this noise to the input so that I have just two amplifiers that are noiseless. And then here at the input, I have my signal coming in and my noise, and then the total noise is just this noise plus this noise referred to the input. So that's F1 minus 1 Ns plus F2 minus 1 Ns divided by G1, gain of the first amplifier, right? And so then you see it's very trivial to find the noise factor. So then F, by definition, is 1 plus the total input referred noise of the amplifier divided by Ns. And so here it's going to be 1 plus F minus 1 plus F2 minus 1 divided by G1. Okay? And so if I simplify this, this is just F1 plus F2 minus 1 over G1. Okay. Now this equation shows us the importance of the noise of the first stage, right? You can see from this equation that the overall noise factor is the noise factor of the input stage. So this is the noise factor plus the noise factor of the second stage minus 1 divided by G1. So this G1 is hopefully large, right, if this is a good amplifier. So the noise of the second stage compared to the noise of the first stage can be much smaller when you input refer it, because it gets divided by the gain of the first stage, right? This tells me that the first stage of a cascade is very important. So if I'm designing a low noise system, I should really spend all my time optimizing the first stage, and I can worry a lot less about the following stages, because incrementally they're going to add a lot less noise. Okay? And this is exactly why we have a low noise amplifier. So that's why an LNA, which is a low noise amplifier, is the first stage of a receiver. And this is true for a communication system, right? So this is my LNA, and then I go to a mixer and to other things. We'll learn later that the mixer noise is typically much larger than the LNA noise, so we can't put the mixer first. We put the LNA to reject the noise of the mixer. You can design mixers that have very good gain, right? So it's not because of the gain that we put the mixer second, it's because of its noise. You might have a fiber optic communication system where this could be a transimpedance amp, where the receiver is a diode that looks like a current source, and we take this input current and we produce an output voltage. And this is, for instance, in a fiber optic communication system. Again, here we want an amplifier that has very good noise performance, because it's the first stage that drives the later stages. Okay? Now, we've derived a formula for two stages. It's pretty easy to generalize this to more than two stages. Okay, so this is F1 G1, this is F2 G2, and what I can do, for instance, is for a three-stage calculation, if I have a three-stage amp, I can first apply the formula to these two stages, right? Formula I've derived, and then apply the formula to all three stages, now as a two-stage, right? So let me just do that. So the noise figure of stage 2 and 3 together, by the calculation we just did, is F2 plus F3 minus 1 divided by G2, right? So let's do a three-stage. Okay, so now the total F is F1 plus F2 3 minus 1 divided by G1. Okay, so now I substitute this expression in here, and what I get is a very simple result. Which you can generalize to more than three stages. Basically, the noise figure of a general cascade is a noise figure of the first stage plus the second stage input referred plus the third stage input referred. Now the gain in front of the third stage is G1, G2, and so on and so forth. Okay, make sense to everybody? Okay, let's do a simple example. And let's take a very simple receiver that has an LNA, a mixer, and a VGA. Okay. So VGA is a variable gain amplifier. It's just a normal amplifier, but it has a control voltage where I can control the gain. When I'm trying to detect a very weak signal, I typically turn the gain all the way high. And so I'm interested in the noise figure under that condition, under the condition of maximum gain. Certain gain in a noise figure, this one has a certain gain in a noise figure, and here. And let me suppose that my LNA gain is 15 dB, and the LNA noise figure is 1.5 dB. Let me assume my mixer has 10 dB of conversion gain, and a noise figure of also 10 dB. And finally, let me assume the maximum gain of my VGA is 70 dB with a noise figure of 20 dB. Okay? So now I'm interested in knowing if I put an input signal, has a certain SNR, what's going to be the SNR at the output, right? How much is the SNR going to degrade because of this system, right? So that's why I need to calculate F. So F is going to be F1, which is I convert from log to non-log, unitless, 1.413, okay? 10 dB is just 10, so that's 10 minus 1 divided by the gain, which is the gain of G1, which is 15 dB, which is 60, plus 100 minus 1 divided by the gain of the first stage times the gain of the second stage. Okay, and when I add it all up, I get 2.4 dB. Okay, this tells me that this system will reduce your SNR by 2.4 dB. Okay, which is actually not too bad. It's pretty tolerable, as we'll see. Okay, so this brings up the question: what does F really mean? You know, what does F translate into? So if, in essence, so before I talk about that, any questions about this calculation? Okay. F really translates into the minimum detectable signal. Okay. So a system designer will come to you and say, look, I can tolerate 10 dB SNR. If you give me a signal that has at least 10 times more signal power than noise power, I can take that and convert it into useful data. Images, sounds, whatever. Okay? So someone tells you that the SNR has to be bigger than 10 dB at baseband. Okay? So you're designing a front end. Okay? So this is your front end. Call it the front end because it's at the front end. And it hits basically an A to D converter. So the ADC takes the signals, digitizes them into bits, and then this is the back end. Again, for obvious reasons. And the back end is like a DSP, and it takes those bits and plays around with them and filters them and produces useful bits. Okay? So the idea is that the spec given to you is at this point I need to have 10 dB signal noise ratio. Okay? So the SNR at the output is the SNR at the input divided by F, where F is the noise figure of the entire front end. Okay? And that, by definition, is the signal power coming in divided by the noise of the source divided by F. That has to be bigger than, let's say, 10. This is the spec that you're given. So given this equation, I can solve for the minimum detectable signal. It's P sig is equal to 10 times F times NS. Okay? Or 10 times F times KT times B. Okay? Any questions? All right. Maybe I jumped a step here. Let me show you why NS is equal to KT over B. Okay? And in fact, this is the way I should have taught the noise of a resistor. So the noise power available from a resistor can be calculated as follows. It's basically Vn squared over R, right? Where R is the resistance value. I don't have a factor of 2 here because this is already an RMS value, right? And so last lecture we saw that this is, so this is my noise source, and I know the maximum noise I can extract is for a matched load, right? So that gives me a factor of 4 here, because I get half the voltage or half the power. So Vn squared we saw last lecture is 4 kTb R divided by 4 times R, and so we see that the noise available from a resistor is just kTb. Okay? So going back to this equation, we see that once you know the noise figure of a system, you know the bandwidth of a system, and you know the temperature, you know the minimum detectable signal. And the only way you can improve things really is either to reduce the bandwidth, which reduces the data rate of your system, or to reduce the temperature, to cool down the whole system. Okay? For extremely sensitive communication, let's say with outer space where the signals are tiny, that's exactly what you do. You cryogenically cool your receiver and you run extremely low data rates. That's why those images from Mars take so long to download. It's not like zip, it's not like DSL. You got to wait a long time. All right, so this equation is so useful that we should also express it in log, because we usually think of the system in log. So this factor of 10 turns into 10 dB in log. F just turns into noise figure in log. And then KT is minus 174 dBm. Okay? Oops, you guys don't see what I'm typing, do you? Okay? And B turns into 10 times log of B. Okay? And so let's do a simple calculation. Let's plug in, let's say for wireless LAN, let's say the bandwidth is about 10 megahertz. Okay? Let's say you're doing about 10 megabits per second, you're averaging 1 bit per hertz kind of spectral efficiency. And let's say the noise figure of your system is 10 dB. Okay? If I plug into this equation, then P sig, which is the minimum detectable signal, is 10 plus 10 minus 174 plus, this is 10 to the 7, or 70. And so I get 70, 80, 90, or about minus 84 dBm. Okay. So this is a very useful number, because you can put up an antenna, walk around your base station, and when the signal level gets less than minus 84, you say, ah, that's it, that's the range of my system. If I want to have more range, I either have to increase the signal power at the source, so I have to amplify the power, transmit more power, or I have to improve my noise figure. Okay? Yes, question.
Yeah, just how can you add dB and dBm directly together? Am I missing something?
You can. Because basically, we're looking at, if you go back to this equation, right? The only thing in dBm here is this term here and this term here. These are just constant factors. So they're just scaling the result. As long as everything is in power, you can do it. Just make sure not, if you have one term in dBm and another term in dBV, obviously it's not going to work. But if everything is consistent, it works. All right. Questions? Okay, so this lecture is too easy for you guys because we just went through one lecture from last semester. So, yes, Al.
So at one point you defined noise figure all in terms of the 50 ohm load, and now you're using just the KTB. So that means that really just the source impedance. Is that right?
I'll clarify it because now we're going to start talking about two ports, real two ports, and we'll see how that comes into play. Okay. So this lecture was kind of a system perspective of noise. When you actually go and build things, you have circuits. So let's go back to circuits. So the first thing I want to talk about is equivalent noise generators. Okay? It turns out that if you have a two-port, and this of course could be an amplifier or a filter or whatever, and it's noisy, you can actually represent this by another two-port, which is noiseless, that has equivalent voltage and current noise. This is Vn squared, this is In squared. And now I can carry on all my calculations with this two-port as opposed to this two-port. Okay? So this is called the input referred noise sources. One's a voltage, one's a current. Now it turns out that this representation is not unique. It would not surprise you that I could also put the noise sources at the output. I still need two noise sources. Or I can have a current noise on the input and a current noise on the output. Or a voltage noise on the input and a voltage noise on the output. Or any kind of combination. The key point is, though, I need two noise generators, and in general they're correlated. Okay? So the important point is that Vn squared and In squared are, in general, correlated. And that makes the math a little bit messy. In this class, for the most part, we'll ignore that correlation, and we'll see that it's not too bad. We get pretty good results. Okay? So now the question is, how do you calculate these equivalent noise generators? Okay. Before I talk about that, let me make sure there are no questions.
Why do we have to have two noise sources?
It's a theorem. It's a circuit theorem. I'm not going to prove it, but you need two. And I can actually show you why you need both. So let me show you why you need both, actually. So I can give you an intuitive proof. Let's say I take my noisy two-port and I short the input. Okay, and let's say that I now look at my equivalent voltage noise, and current noise. Well, you can see that the current noise gets shorted. And so if I'm looking at the output, let me observe the output noise. In this case, let me also observe the output noise. And of course, the output noise has to be the same, because this is an equivalent representation. If I had only used a current at the input, you could see that I could not get any output noise. And so current alone is not enough. I have to have a voltage, right? To see why you need a current, of course, you leave it open. So this is test 1. Test 2, I'm going to leave it open. And again, this is the noisy 2-port. And this is the noiseless 2-port. Again, here I'm going to take my noiseless 2-port, and with my equivalent generators, I leave the input open. Now you can see that the voltage source is dangling. It has no effect on the circuit, and the total output noise in this case is only due to the current. So again, I'm going to observe output noise, and ditto here. And so here you can see that the total current goes to the input. So here I can say that noise is due to IN squared only. Here I can say that noise is due to VN squared only. Okay? So this is a nice, first of all, this proves that you need both to answer your question, but it's also a nice procedure to calculate the equivalent input and input noise, current, and voltage. Okay. Any other questions? Okay, so it's always good to do examples. Let's look at our BJT noise sources. So our bipolar transistor, let's draw the equivalent circuit. So this is C pi, this is R pi, this is IB squared, base current noise, this is RB, this is VRB squared, this is C mu, this is GM V pi, this is V pi, this is RO, C squared. Okay. And I'm grounding the emitter just for simplicity. So now I'd like to represent this BJT by a black box, which is everything in here without the noise sources, and then an equivalent voltage and current noise source. Okay? So let's follow this procedure. Let's first leave the BJT base open. And observe the total noise at the output. Okay. So if I look at the output with the base open, obviously this won't have any effect, and this current source directly feeds to the output, right? And this current source here feeds to the output with a current gain of the transistor, which is beta squared. So the total output current noise flowing into a short circuit would be IC squared plus beta squared IB squared. Okay? And if I now look at this equivalent system, if I also short this, this voltage source is also dangling, and so the only current going into the BJT is this guy, which we call IN. And IN squared gets a gain of beta squared to the output. So this is equal to beta squared IN squared. Okay? So then the equivalent input noise of a BJT is therefore IB squared plus IC squared divided by beta squared. Clear to everybody? Okay. Let me now calculate Vn squared. So if I short the input, then of course In squared plays no role. The current just flows in this loop. And let me short the output and observe I out squared. So the output current, let's say for Vin, is going to be the input current times beta squared. Well, Vin squared divided by the input impedance, which is going to be Rb plus Z pi squared, times beta squared appears at the output. Okay. Now if I look at my transistor, for my transistor, if I short the input, IB squared essentially plays no role, right? If we want to be technical, we would say, oh, there's current division between RB and Z pi. Let's forget about that. So IB plays no role. VRB gets the same gain that we just calculated for Vin, and again, IC just flows to the output. So here, I equate this to beta squared VRB squared divided by the same gain plus IC squared. Okay. Questions? Is clear to everybody? So now I solve for Vn squared, and Vn squared is just VRB squared plus IC squared times Z pi plus RB squared divided by beta squared, or approximately VRB squared plus IC squared Z pi squared over beta squared, because Z pi is usually much larger than RB. Okay? In other words, I can now say that my BJT, my bipolar transistor, is a noiseless transistor, and in particular at low frequencies where Z pi is just R pi, Vn squared just becomes VRB squared plus IC squared. Z pi is just R pi, so this is R pi squared divided by beta squared, but R pi over beta is Gm, so this is VRB squared plus IC squared times divided by Gm squared. Okay. And also, if I look back to In squared, a couple slides back, you can see that In squared is IB squared plus IC squared divided by beta squared. So again, at low frequency, we can just say it's the shot noise of the base current. So this gives us 2QIC divided by beta. Okay. So that's the way you calculate the input noise, voltage, and current for a bipolar transistor. And so you might say, big deal. What are you going to do with that? Well, the nice thing about having the input generators is it gives you a lot of intuition. Comparing the voltage noise to the current noise relative to the source impedance tells you a lot. Let's see why that is. Okay, so let's look at now the role of the source resistance. So this is partly going back to Al's question. So this is my noiseless 2-port. This is the equivalent noise here and here. Okay, let's suppose that Rs is equal to 0. In other words, I voltage drive this. Well, if Rs is equal to 0, In squared flows through the source, and only Vn squared is important. Okay? On the other hand, if Rs is equal to infinity, I have a very high source impedance, then the opposite is true. Vin tends to dangle and not do anything, can't generate any input current because of this high resistance, and In squared is the only important. Okay? So, for instance, a MOS amplifier, if you drive it with large RS, because you can, because the gate is essentially an open circuit, then you really care about In squared of a MOS. Okay? On the other hand, if you have a low impedance, let's say Rs is low, then you really care about Vn squared, and for bipolar, we just showed that Vn squared is basically VRB, and if I do good layout, I can make RB very small, plus IC over GM squared. And if I make GM large enough, if I burn enough current, I can make Vn very large. Okay? So already we see that these input generators give you some intuition for what's going on. What's more interesting is what's the optimal Rs. In other words, given an amplifier that has Vin and In, we can see it's very likely that there's going to be an optimum solution, an optimum source impedance that will minimize the overall noise. Okay? For these two special cases, it's obvious, right? If you only had input voltage noise versus input current noise, then you know what the obvious solution is. But in general, what's the obvious answer? Okay? Okay, so to answer that question, we need to do a little more work. What we're going to do is we're going to derive the equivalent input noise voltage. In other words, I'm still not happy having two sources. I'd like to just have one source. Okay? And maybe for homework or as a practice, you guys can also do this for current. So the idea is I'm going to now take my two-port that looks like this, and for a given source impedance, I'm going to transform it to, so this is Rs, Rs. I'm just going to find the noise equivalent. Now, I didn't have to choose voltage. I could have also chosen current. That's why I encourage you guys to redo this exercise for the case of current. Okay? So let's calculate in this general case. So this is In squared. This is Vn squared. Let's calculate the total output voltage here due to these two noise sources. Okay? And stop me if it's not clear. First of all, Vn squared sees the voltage gain of this amplifier times basically Rin, basically the voltage divider. So times Rin divided by Rin plus Rs squared. Okay? So if I know the voltage gain, I know what V out squared is due to V in. Okay? That's pretty simple. And then the voltage noise of Rs also sees the same exact gain. So VRS squared is also multiplied by the same thing, times AV squared. Okay? Okay, that's easy enough. What about the current? Well, the current, you can do a current divider, right? You can say that the fraction of the current that goes into the input times the input impedance times AV squared also produces an output. So that would be, so if I take In squared, to find the fraction that goes into the input, I take Rs over Rs plus Rin squared. Okay? And then that times Rin squared is the input voltage. And then that times AV squared is the output. Okay? Let me make sure this is what I get in my notes. Yeah, that looks right. Okay? So this is the total output voltage, and you'll notice that this factor, I can move this in here and this out, and they all have the same factor, Rn divided by Rn plus Rs. So I'm going to rewrite this as simply V out squared is Vin squared plus In squared Rs squared plus VRS squared, all multiplied by Rn divided by Rn plus Rs squared, all times AV squared. Okay, so all I've done is just reorganize this expression. And now you can see that I can represent the noise of the two-port. This is the noise of the source referred to the output. The noise of the two-port looks like an equivalent voltage noise, also voltage gained to the output. So I've found a very important equation. What I was trying to find is the equivalent input noise voltage is Vn squared plus In squared Rs squared. Okay? Yes, question.
You mentioned earlier the V and IN are correlated in many ways. Can you put them together like this?
Okay, I've ignored correlation. Yeah. Yes?
You really don't need, when you have a finite source impedance, you don't really need both of the I and the VN. Because even though they're correlated, you don't need both of them to quantum the input, because you don't have an Rs equal to 0 or Rs equal to infinity.
You do need both. Right? I mean, at the end of the day, if I don't have both, I'll get the wrong answer.
If you have an Rs equal to 0 or infinity.
So you're saying you don't need both. Like if you just know Vn, you're set.
Yeah, if you have an Rs.
Okay, maybe we could talk about that after class, because it doesn't make sense to me. You need to know both. They're independent of each other, right? If I know Vn, I don't know In.
No, you can model both when you're DEQ.
That's exactly what we've done here, right?
Yeah, but this doesn't have any correlation inside.
So your point is,
No, there's no correlation, that's what I'm saying. You've not ignored anything.
yeah, up to now I haven't, but I will later. Yeah, I'm sorry, I misunderstood your point. Okay. Your point is that up to now we haven't used the fact that they're correlated or not correlated. You're absolutely right. Yeah, the results right now are general. The generality will break down soon. Okay. All right. Okay, well, what I've done now is I've calculated the equivalent noise of my two-port, and going back to my equation for noise figure, remember it's just 1 plus noise of the amplifier at the input divided by noise of the source. Okay? So that means that my equation is simply that. Okay? So this is a general equation for the noise figure of a two-port when the source resistance is Rs. Okay? Okay. So now it's very common. So I want to now find the optimal source resistance. It's very common to represent Vn squared by 4kT Rn times B, the bandwidth, where Rn is just a fictitious resistance that generates the same noise as Vin. Obviously, this is only going to work if Vin is actually white, right? But you can make this argument that if it's a narrowband system, certainly the noise is flat in the bandwidth of interest. And likewise, I can say that In squared is 4kT Gn times B. Okay? So Rn and Gn are kind of fictitious. They're just two parameters that are the same as Vn squared and In squared. Okay? They just make the math a little easier. You don't have to keep writing squared bar, squared bar. So if I just plug in, V equivalent squared is 4kTb times Rn, Gn Rs, and noise of the source is just proportional to RS. And you could see the 4kTB cancels out of the numerator and denominator. Okay? And then I could write this as 1 plus Gn Rs plus Rn over Rs. Okay? So this is an equation which shows us that the noise figure of our amplifier is a function of the source resistance, okay? And it's proportional to the source resistance and inversely proportional to the source resistance. Whenever you see that, you know there's an optimum point, right? And so we take the derivative of f with respect to Rs. We get Gn minus Rn Rs squared. Set it equal to 0. And solve. So we find Rs opt is equal to Rn over Gn square root. Or if I plug back in the definition for Rn and Gn, it's Vn squared divided by In squared square root. Okay? Now, going back a few steps to the question about correlation, this result only works if things are not correlated. I made a mistake in answering Amin's question. Actually, we are neglecting correlation. Okay, sorry. I'm all confused. Anyhow, at the end of the day, though, we have a very important result that this is the optimum source resistance that gives us the minimum noise figure. Okay. Now what's interesting about this result is that, first of all, Rs opt is not necessarily equal to Zn complex conjugate, right, in general. You can actually design things and make this happen, but in general they're totally independent. That means that if I match for power, I don't necessarily get the best noise performance. And so there usually is a trade-off between matching for noise versus matching for gain. Okay? Any questions up to here? That's pretty clear. Yes. Okay.
This slide, you have the equation for f. Why, if we take Rs to 0, why does f go to infinity?
That's because I have it's because of the voltage noise, right? So this term goes to infinity. That means that, so that's a good question. Let's look at the sanity check. So I have a voltage noise and I ground it. And if I look at, so F is the SNR at the output. So what's happening is we're getting no signal gain, but we're getting finite amount of noise gain. Why are we not getting signal gain in this case? That's a good question.
You said no input for input noise, right? So your initial SNR is perfect.
Oh yeah, that makes sense. Yeah. Okay, thanks. Yeah, if you don't have RS, there's no input noise. So that makes sense. Yeah. Thanks, Al. Any other questions?
If the input between is real, then Rn is 1 over G. Rn is 1 over Gn, is that right?
No. Remember, Rn and Gn have nothing to do with the input impedance of the transistor. Of course, there's some relationship, but in general, Rn is the equivalent input noise voltage, right? And Gn is the equivalent input noise current. Now I'll give you an example of where they're totally uncorrelated. Let's say your device only has output noise and no input noise. So real part of Zn, let's say the device is unilateral. Then real part of Zn, right? Let's say that there is no real part of Zn. Let's say it's a capacitive input impedance. But there still is a real part of input noise, voltage and current, because when you input refer the output noises, you get an Rn and a Gn. That make sense? Okay. Okay, so the next thing we can calculate is the actual F-min of the device. In other words, if we do this optimum matching, what do we get? So in general, this is the equation. And so this is basically RS equal to RS opt. So I plug in RS opt, I get 1 plus Gn. RS opt is basically square root of Rn over Gn plus 1 over that, Gn Rn times Rn, or 1 plus 2 geometric mean of Rn and Gn. Okay, so this is the optimum, this is the lowest noise figure that you can get with this two-port. And it's a very important metric because imagine you have two transistors and you're trying to decide which one to use for your LNA. Obviously, you use the one that has a better F-min. Not quite obviously because the gain also matters, as we'll see later on. But as a first-order metric, if the gains are equal, you'd pick the transistor that has a better F-min.
But that means that you need to be able to change RS to whatever you want, which is not true in most cases.
Well, that's why we can impedance match, right? Yeah, you don't get F-min unless you drive it with the right source impedance. And so you have to do impedance matching. Okay? Any other questions or comments? All right, well, there's actually a very nice relationship between F and F-min. So let's see if we can derive that. Let's take the difference between F and F-min. So F in general is GnRS plus Rn over Rs plus 1, but the 1's will cancel out, and I just end up with minus 2 Rn Gn. Okay? And now let me factor out this term Rn over Rs. So here I get 1, here I get Gn Rs squared over Rn, and here I get minus 2 Rs over Rn, Rn Gn. Just doing a little bit of algebra. So this is Rn over Rs. This is 1 plus. This you recognize, this ratio, as Rs opt. The whole thing is squared. And then this is 2 times Rs, and here this is going to give me square root of Rn over Gn. So that's Rs opt. Okay? And then you can recognize this as a perfect square. And so this becomes Rs over Rs opt minus 1 squared. Or I can write this as Rn times Rs G opt minus Gs squared. Okay? So this is F minus F-min. So let me add F-min on the right-hand side. And then I have this really nice equation which tells me that in general the noise figure of a two-port is F-min plus something. So I can never get below F-min. We already knew that. But what's really interesting here is it tells me that if I give the optimum source impedance, this term goes to 0 and I get F-min. Okay, I knew that as well. But it tells me how quickly the noise increases as I move away from the optimum source impedance. Basically, this is the distance between optimum source impedance and the actual source impedance squared, right, times this factor Rn Rs. Okay? So sometimes people call Rn the noise sensitivity parameter because it tells you that if you have two devices and they both have the same F-min, but one has a bigger Rn than the other, certainly you'd use the device with the smaller Rn. Why? Because the device with the smaller Rn is less sensitive to variations of Gs from Gs opt. Okay? So even if your design is a little bit off, temperature changes, or you have process variations, you still get a nice low value of F-min, close to F-min. Okay? Any questions or comments? All right, so let's go back to that BJT and apply what we've learned. Okay, for a bipolar transistor, we calculated that Vn squared is VRB squared plus IC squared divided by GM squared. And let me just write this out in terms of 4kT BRB plus 2QICB, that's the collector shot noise, divided by GM squared. And I found that the noise, equivalent input noise current, is roughly the base shot noise. Okay. So now let me calculate F in general, right? I have this expression that F in general is 1 plus GNRS. So this gives me 4kT RB. Okay, I'm doing it the longhand way in my notes. Okay. Plus 2Q ICRS squared divided by beta 4kT RS. Okay. So this is the noise figure of a bipolar transistor. If we plug in just IN and VN, right? It's 1 plus VN squared plus IN squared times RS squared divided by noise of the source, which is 4kT RS. Okay. And now you can see that lots of cancellation goes out. Let's cancel out this common factor of 4kT. 4kTB. I've already canceled the B out, it looks like. So this term here gives me RB over RS. Okay. This term here, GM is also, I can write GM as IC over KT over Q, right? And if I simplify this term, I get 2GM RS. And this last term, if I simplify it, becomes GM RS divided by 2 beta. Okay, so now you can clearly see that you can improve the performance, the noise figure of a transistor as a function of bias, right? So let me just say that F is a function of the bias and a function of RS, right? So the calculation we just did told us what the RS opt is, but it didn't tell us what bias point to choose. And you can see now that by choosing the bias point appropriately, I can also minimize F to begin with before I even apply the optimum source. So for instance here, if I make GM sufficiently large, right, this term will go away, but then this term starts to dominate. So there's probably an optimum GM value here that balances these terms out. But this term here is independent of bias. So this term is actually pretty problematic. That's why if you look at a transistor, the way to optimize its performance is to lay it out in such a fashion as to minimize RB. Okay? So, getting lazy here towards the end of the lecture, so let's use some slides. Okay, so this is the simple layout here of a single transistor, right? And you can see where RB is coming from. RB is just the resistance to get from the basically the. So this is actually bad figure. So RB is this resistance, right? And part of it is also this resistance, but what really dominates is, so most of the transistor action actually happens, yeah, this figure is actually wrong. let me redraw it. Okay. So here's my transistor. So this is my buried collector. And this is my base resistance, actually. Maybe the figure was right after all. So this is my emitter. This is my base. Okay? And so I have to get to this vertical junction and I have to go through this region. So this is the base resistance. Obviously, if I contact it at both sides, I reduce the resistance. I cut the distance in half and I have 2, so I get them in parallel. I can also cut the resistance by adding multiple fingers to my transistors, right? So the way you lay out a bipolar transistor has a lot to do with minimizing RB. Okay. So some of the interesting things about BJT sizing. First of all, the GM is only a function of IC to first order, not size. That's actually one of the really nice things about a bipolar transistor, that I can just increase the current and get a better transconductance and keep the transistor as small as possible to minimize its capacitance. Well, at what point does that break down? Why can't I take a tiny, tiny, tiny bipolar transistor and just run an amp of current through it? Why is that? Yeah, Kirk effect, right? Kirk effect ultimately will limit the performance. So the limit is the Kirk effect. So I can't arbitrarily trade power for performance in a bipolar. The other nice thing about a bipolar is that Ft is determined by a vertical dimension. This is the base. And again, for small currents, for reasonably small currents. And so the performance is also fixed. Even if I scale the device, I don't affect its Ft to first order. This is if the base transit time dominates. Okay. So what I can do is increase the emitter area to lower RB. And as I increase the emitter area, I get more capacitance, right? But if I bias my device so that the Ft is dominated by the base transit time, to first order, I won't hurt my frequency performance too much. And because my GM is independent of the size, I'm just lowering RB, which means I'm improving its performance. Okay? So that's why when you're designing a bipolar transistor, you basically start out with some kind of, so if I'm going to size, kind of just summarize here, a bipolar. This is a curve, this is Ft versus the collector current. You can see that I don't want to have more current than this, because if I have more current, it's not really helping me. I'm starting to lose performance. In fact, it turns out that this drop is quite rapid in modern technology. So I definitely want to operate somewhere here. And I make my device large enough so that RB is small enough so I get good noise performance out of it, but that the junction capacitances start to hurt my performance. So you can see there's a nice trade-off that you can make with a bipolar transistor. Okay. Any questions or comments? Yes.
The eighth equation earlier for BJTs, I thought that's for low frequency only.
Yeah.
And can you take into account when you have bigger junction and the capacitance bigger and so on, how the F change?
You can do that for homework. I'm sorry?
Can't you just multiply by the frequency response? You have the input
Mm-hmm.
frequency response and not the output, so just multiply.
Well, the problem is that IN and VN have frequency dependence. We ignored that.
You just integrate something that's frequency dependent by frequency response and just integrate. What's the problem?
So this derivation that we did here, right? We ignored the frequency dependence of these terms, right? So just to keep the algebra simple for class, you know. But it's, I mean, the theory is all the same. You can apply it. It just gets messier. Okay, next.